Hello, everyone. I'm Klaiber. I'm with Bosch Research, and today I'm going to tell you something about how to enable cross-domain communication, in particularly how to bridge the gap between AI and hardware engineers. This workshop is about building accelerators. In a sense, building accelerators is pretty similar to building an engine for a car. So most people would think the more power, the better. And most engineers I know, they really like to build high performance, high-end things. So but what if the system or the car you have to build looks similar to this? Certainly the engine on the left side would not be the right choice for a number of reasons. So what is the gap between hardware engineers and AI engineers that I'm talking about? So in our opinion, it is a lack of an API or a language for early performance evaluation for AI and hardware engineers. So you don't want to implement or design for months on both sides to find out that they finally do not fit together and do not achieve a good performance together. If you have ever been in the role of a system architect, you will especially feel that there is a need for a methodology like this. Because then everybody will nag you with questions like, what are the operations that are actually worth to be accelerated in hardware? Management might ask you, oh, what is the chip area versus accuracy versus execution time? Can you please quantify? We need this for our cost calculation. And last, some slick project manager might come along and ask you, why don't you just use the hardware that we have used in the last project and adapt the algorithm to it? That might be much cheaper. Well, we're not claiming to have found the answers to all of these questions. So we haven't solved 20+ years in hardware software co-design research. The methodology we want to encourage is for hardware people to build lightweight, abstract execution models really before writing the first line of RTL code. And by abstract, I mean focusing on the timing details rather than on the implementation details. And AI guys should use state-of-the-art tools such as neural network compiler stacks, for example, TVM, to build abstract workload descriptions. If you plug these two things together, then two new scenarios arise, really at the beginning of the project. So on the left, you can see the hardware designer again. So if he has a new idea for his hardware topology, any new idea in the hardware, he uses the model that he has built plus the abstract workload description, which comes from the right from the AI designer, and can at any time execute it and check whether some hardware modification makes sense and quantify whether it should be implemented or not. If you look at the right cycle, if the AI designer has a new idea, for example, for integrating a new neural network layer or a new function, he describes his idea, for example, in Keras or TensorFlow, brings it through the neural network compiler stack and executes it on a virtual hardware model, which has been described by the hardware people, and immediately gets a performance result back. So the AI people can directly quantify how fast neural network architecture performs with the system description the hardware people came up with maybe a day ago. The changed color code here now shows also the changed skill set and the changed responsibilities both teams have. So the hardware people are, for example, now also responsible to help building compiler passes that utilize the hardware they came up with in a good way. On the other side, the AI people, because they use the hardware, they also need to be aware of the properties of the hardware. So for example, how are the memories distributed and how many cores are available. I would also like to give you a short idea of a proof of concept tool flow that we have built. So what you can see here is an abstract workload model built with TVM from a neural network. and it is executed on a virtual hardware model in a proprietary simulation tool. So basically, you can check the execution on a cycle level and check the bus accesses also on a transaction level. Directly after the execution, then you get results on the target hardware on a layer basis and can evaluate how long the execution of each neural network layer took. In summary, we can conclude that hardware-software co-design for embedded systems in large teams is challenging. We also consider performance evaluation in early stages of the project crucial, as well as human communication. To improve all of this point, we propose supporting the design process by the following points: formalizing of system, hardware, and software description, an end-to-end API from hardware to use case, for example, AI, and virtual models as communication medium. And this essentially is what this workshop is about. It's about languages and tools. Thanks for watching this video. I'm really looking forward to the discussion with you in the workshop.